Okay, welcome back to my Math 1500 Applied Business Mathematics from Connecticut State Community College. Today we're going to look at exponential functions and models. We'll do some exponential regression as well. I want to begin by a quick review of our exponent rules or laws of exponents. And you see that I've put on here the basic rules, right? So b to the x times b to the y is b to the x plus y. A little illustration there, if I have 5 squared times 5 cubed, 2 plus 3 is 5, so that's 5. Whoops, that's 5 to the 5th. Okay, or x squared times x to the 4th would be x to the 6th. The exponent tells me how many times I'm multiplying. If I multiply by 5 twice, then I multiply by 5 3 times. I'm multiplying by 5 a total of 5 times. X squared times x to the 4th would be x to the 6th. If I have b to the x times b to the y, or divided by b to the y, if I'm dividing, I subtract the exponents. So if I have b to the 5th divided by b to the 3rd, b times, I'm sorry, that's b times b times b times b times b is what b to the 5th means. I'm multiplying by b 5 times. B to the 3rd, so these b's cancel, these b's divide out, these b's divide out, and notice I've only got b times b, or b squared, left, so 5 minus 3 is the exponent of 2. The exponent tells me how many times I'm dividing, so in number 3, 1 divided by b over x, or 1 divided by b to the x, is b to the negative x, because notice the exponent is the opposite, so I'm doing the opposite of multiplying by x, I'm dividing. So 1 over b squared would be b to the negative second. Conversely, b to the negative second is 1 over b squared. I've got another way to show you that in a minute, but now b to the 0 equals 1. We often say that anything to the 0 power is equal to 1 just because, but here's why. Really, b to the 5th is not b times b. We always start with 1. Whenever we multiply, we start with 1. So b to the 2nd means 1 times b times b. B to the 1st means 1 times b. B to the 0, I start with 1, and I do nothing with that. So b to the 0 is 1. So actually, go back to number 3. If I go back to number 3 here, 1 over b squared is the same as b to the 0 over b squared. And to use rule number 2, 0 minus 2 is negative 2. Okay. B to the x to the y is b to the xy. So suppose I have b squared cubed. That means I have b squared times b squared times b squared. And rule number 1 says I would add these up. 2 plus 2 plus 2 is 6. So that's why b to the x to the y is b to the xy. bc to the x is b to the x, c to the x. That's simply the exponent goes both to the c as well as to the x. Number 6, that's true if I'm multiplying b times c. Number 7, that's true if I'm dividing b times c. So if I were to have, say, 7/3 squared, that's 7 squared over 3 squared, or 49 over 9. Quick walkthrough rules of exponents. An exponential function is anything that can be written in the form of y equals a times b to the x. A is the initial value. The reason that a is the initial value, that's the value when x is 0. And like we set up above, b to the 0 is 1, so that would just be a. A is the initial value. Okay? B is what we call the base of the function, or it's the constant multiplier. That's what we consistently multiply by. A little bit of evaluation here, like we've done previously in previous videos with linear functions and quadratic functions. If f of x is 2 to the x, then f of 2, I'm going to replace the x with 2. f of 2 is 2 squared, or 4. I'm going to go down here to f of 0. That would be 2 to the 0, which is 1. F of negative 3 would be 2 to the negative third, which is 1 over 2 to the third, or 1/8. Now for part D here, this is 2 to the x plus 3. But now remember from my rules up above, that's 2 to the x times 2 to the third, 2 to the x times 8, because 2 to the third is 8. So I could write this then as 8 times 2 to the x. Okay? Because I use my rules of exponents. Number 2, notice my function, f of x, is 2 times 3 to the x. To find f of 2, I replace my x values with 2. 3 squared is 9, times the 2 would be 18. F of negative 3 would be 2 times 3 to the negative third power. But remember, that would be 1 over 3 to the third, or 2 over 27. F of 0 is 2 times 3 to the 0. Now be careful, I don't just get 1. 3 to the 0 is 1. 2 times 1 would be 2. So f of 0 equals 2. F of x plus 2, 2 times 3 to the x plus 2. I'm going to use my same rules here that I used in part D up above. 2 times 3 to the x times 3 squared. So 2 times 3 to the x times 3 squared, which is 9. 2 times the 9 is 18. So I have 18 times 3 to the x. Okay? We're employing our rules of exponents. What does the graph of an exponential function look like? So an exponential function, we might recognize this first one from up above. Okay? F of x equals 2 to the x. F of 2 was 4. F of 0 was 1. If x is 0, we had 1, so here's my point, 0, 1. F of 2 was 4. If x is 2, y was 4. So we have the point 2, 4. You'll also recall that f of negative 3 was 1/8. Whoops. A lot of scrolling here. 1, 2, 3, negative 3, 1/8. So that's the point, negative 3, 1/8. What you'll notice is that the graph increases exponentially. It increases at a faster and faster rate. Now, something that's going back here, the graph will get lower and lower and lower, but it's never going to even get to the x-axis. The x-axis is a horizontal asymptote. So I'm going to label y equals 0 as a horizontal asymptote, because the graph will get closer and closer but never touch it. It is essential to me. I insist that students, that you always draw and label the asymptote. I also expect that you're going to give me at least 2 or 3 points. Okay. So number 4, if x is 0, I'm going to make a little table of values here. If x is 0, we have 2 times 3 to the 0. 3 to the 0 we said is 1, times 2 would be 2. Let me fix my table. X, f of x, we said if x is 0, y is 2. If x is 1, 3 times 1 is 3, times the 2 would be 6. We have 0, 2, 1, 6. And if I put in, say, -1, I would get 2/3. If we go back this way, the graph will get closer and closer and closer to the x-axis, but it will never touch it. As we move forward, it's going to get steeper and steeper and steeper. I am happy if you give me 2 points, but you also must every time draw and label that horizontal asymptote. You'll notice that for numbers 3 and 4, the graphs are increasing. Okay, this graph is going up and up and up. We call that exponential growth. Number 5, you'll notice we have 1/2 to the x. So if x is 0, y is 1. If x is 1, y is 1/2. If x is 2, y is 1/4. You'll notice that these are getting lower and lower and lower. In fact, if x was, say, -2, f of -2 is 1/2 to the -2, and that's going to be the same as 2 squared, or 4. -2, 4. So you'll notice that this graph is getting lower. If I went backward, it would go up high, but as I come forward, it's getting closer and closer and closer to the x-axis. The x-axis is still a horizontal asymptote, y equals 0, and the graph is getting closer and closer and closer to it. This graph is getting closer to the x-axis. It's getting smaller. As x gets larger, y is getting smaller because this b value is between 0 and 1. Number 6, same thing. If x is 0, 2/3 to the 0 would be 1, times the 3 would be 3. So I have the point 0, 3. If x is 1, I put 1 in for my x. 2/3 times 1 is 2/3, times the 3 would be 2. If x is 1, we have 2. And notice my points are getting smaller and smaller, getting closer to my x-axis again. It is difficult when graphing these functions to make a distinction from curve to curve to curve. It's why it's so crucial that you must always draw and label the horizontal asymptote. You must always draw, plot, and label at least 2 points. Okay? Now, in numbers 5 and 6, you notice that these graphs are getting smaller. That's because the b value is between 0 and 1. These are what we call exponential decay. Okay, so these two functions, the first two that we graphed, numbers 3 and 4, were exponential growth. 5 and 6 are decay because the values are getting smaller. The graphs are getting smaller. So let's look at some characteristics of exponential functions. You'll notice these above. There's always going to be that horizontal asymptote. Okay, we're always going to go through the point 0a and 1ab. Always, every time. If b is greater than 1, the graph is increasing, and that's exponential growth. I typed here, I would say if b is less than 1, it's always going to be the case that b is going to be greater than 0. So we might say if b is less than 1, it's better to say if b is between 0 and 1, the function is decreasing, we have exponential decay. All right. So I just have a few things. We talk about lines, right? If I have 2 points, I should be able to find the equation of a line that goes through those 2 points. Similarly, if I have 2 points, I should be able to find the equation of the exponential function that goes through those 2 points. Y equals a b to the x. If x is 12, if x is 2, y is 12. So that gives me the equation 12 equals a times b to the second. I also have 5 and 96. If x is 5, y is 96. Now I'm going to write this equation above. Y is 96 when x is 5. With linear functions, we would subtract the bottom equation from the top. These are exponential. We're going to divide the top equation by the bottom equation. So 96 divided by 12 is 8. A divided by A is 1. B to the 5th divided by B to the 2nd is B to the 3rd. So B to the 3rd equals 8. To solve this, I'm going to take the cube root of both sides, and B, cube root, B is the cube root of 8, or 8 to the 1/3 power is 2. The cube root of 8 is 2. So my equation is y equals a times 2 to the x. I'm going to take either the 212 or the 596, and I'm going to plug that in for x and y again. So if y is 12, when x is 2, 12 is equal to a times 4. Divide both sides by the 4, and a is equal to 3. So I have the exponential function y equals a times b to the x. B is 2, a is 3. Y equals 3 times 2 to the x. And there's my exponential equation. Let's do another one, number 8. Find the exponential function that passes the point negative 220 and 2/5. So this one's got a little bit extra wrinkle in it. Y equals a times b to the x. So 20 is a times b to the negative second. 5/4 is equal to a times b to the second. I'm going to flip those around. 5/4 equals a times b to the second, and we're going to divide that by 20, a times b to the negative second. So I have 5/4. I can do this on the calculator. 5/4 divided by 20 gives me that decimal. I'm going to change that to a fraction. So 1/16 equals, now the a divided by a is 1 again. B to the second divided by b to the negative second is b to the 4th, because 2 minus negative 2 is 4. B to the 4th equals 1/16. Now I want to take the 4th root of both sides, and I get b. So I have 1/16. Now I can just press what I want to do here. Well, let's not do that. 1/16 to the 1/4 power is 0.5, or 1/2. So b is 1/2. So 20 equals a times 1/2 to the negative second. I put the b value of 1/2 into this equation here. Using our rules of exponents, 1/2 to the negative second is 2 squared. So 20 equals a times 2 squared, which is 4. So 20 equals a times 4. A will equal 5. So my equation is y equals 5 times 1/2 to the x. Those take a little bit of work. Let's look at number 9. Number 9, notice that the first point is 0, 15. Y equals a times b to the x. I like that one. Y equals a times b to the x, but x is 0 when y is 15, but b to the 0 is 1, a equals 15. When I have a point where x is 0, I know the y value is simply just a. This is going to make things easier. Y equals 15 times b to the x. Now when I plug this x and y in, y is 25 when x is 10. b to the 10th is 25 over 15. I could reduce my fraction. I'm going to need my calculator to take the 10th root of both sides anyway. So let's just use my calculator and do 25 over 15. We're going to raise that to the 1/10th power, and we get 1.052. So b is 1.052. So my equation is y equals a, which was 15, times 1.052 to the x. And there's my exponential function. Okay. Now 1.052, that's the same as 105.2%. That's a 5.2% increase for each value of x. That's going to come into play in number 10. Number 10, I'm going to make a couple of connections to things that we're going to do in the future, as well as some adjustments. The minimum wage. In 1939, the minimum wage was 25 cents an hour. Imagine that. You work a 40-hour work week and make $10. 25 cents an hour. Currently, in 2025, whether we like it or agree with it or not, the federal minimum wage is still set at $7.25 an hour. A lot of states have increased that and have adjusted that for themselves, but federally, the minimum wage has not been increased from $7.25. Find the exponential function that models the federal minimum wage as a function of time. Now, the first thing I want to do is I want to adjust those years. Rather than use 1939 and 2025 as my x values, I really don't need to find the minimum wage since year 0. We've done an adjustment like this before. X is the number of years since the year 2000. What I'm going to do is I'm just going to let x represent the number of years since 1939. 2025 minus 1939 is 86. It's currently 86 years since 1939. So if I use those if I use those x values, 0 and 86, and I jump into my equation, y equals a times b to the x, I know that my a is 0.25. So y is 0.25 times b to the x. Now if I use the other point where y is 725 and x is 86, I'm going to divide both sides by the 0.25. b then, b to the 86 is 7.25 over 0.25. I could divide that and get 29, or I could just leave it. To solve for b, I need to find the 86th root of both sides. I need to raise both sides to the 1 over 86th power so that those cancel, and I just get b. So back to the calculator. 7.25 divided by 0.25. We're going to raise that to the 1/86th power. 1.040. So 1.04. So I'm going to write it down here. Y equals a 0.25 times 1.04 to the x. Okay, so that's the equation that we needed for part A. The average annual rate of increase. Notice that B is 1.04. We are multiplying this by 1.04. 1.04 is the same as 104%. 100% is 1. Okay, so every year we could say it's as if the minimum wage is 4% more than it was before. So if I multiply by 1 by 100%, that's the same. So this is a 4% annual increase. It's an increase of 4%. 1.04 minus the 1 is 0.04. That represents a 4% increase. So if the minimum wage has increased from $39 to $7.25 an hour, or 25 cents an hour to $7.25 an hour since 1939, that's as if the minimum wage has been increasing at 4% per year. Let's look at some more growth and decay and what's the rate of increase. In number 11A, my A value is 12.3. That's my initial value. My B value is 1.156. That would be growth. B is 1.156. That's greater than 1, so it's growth. What is the rate of growth? 1.156 minus 1.00 is 0.156. If I change that to a percent, that's 15.6. So this is a growth of 15.6%. B, you'll notice that my B value, 0.853, is less than 1. So that indicates that this is decay. Now what's my rate of decay? 0.853 minus 1. 0.853 minus 1 is negative 0.147. Negative because it's decay, it's shrinking. 0.147 is the same as 14.7%, but that's a negative. So I have this is decay of 14.7%. We're decaying at a rate of 14.7%. I don't need to rewrite the negative because the word negative is included in the word decay. Some applications that we're actually going to spend quite a bit of time on in our next unit is looking at investments and growth and whatnot. For right now, I'm going to give you the function A. That's our future value or amount in the future is equal to P, which is our principal, times 1. That 1 is the 1 for 100% change, which is nothing, no change. Plus my interest rate divided by n, the number of times that I'm compounding per year, times n, those compounding amounts or periods, times t, where time is measured in years. So number 12, I'm going to invest $2,500. If I multiply that, that would be no change. But an interest rate of 7.2%. Notice my 7.2% got changed back to the decimal, 0.072. We're compounding that monthly, so my n is 12 in both places. What's my account worth in 15 years? It's a little bit of complication to that function, to that formula, but what's nice is that the calculator, this function is perfectly set up to go right into the calculator. 2,500 times 1 plus 0.072 over 12 to the 12 times 15 power is 73.3798. So if I take $2,500, I put it into an account that pays 7.2% interest compounded monthly. At the end of 15 years, my $2,500 will be $7,337.98. If I'm fortunate enough to find an account, probably an investment account, where that interest is going to be compounded continuously, the formula changes. The future amount, A, is equal to P, the principal that I invest, times E to that interest rate for T years. There's no N because we're not compounding monthly or annually or weekly, but we're compounding continuously. So now if I invest $2,500 compounded continuously, getting 7.2% interest for 15 years, we'll see what that amount will be. When I use the calculator, let me clear my screen. 2,500 times E. I want to use second E. That's right here. So my natural log button turned red. Right above it in blue, it says E to the X. So that's 2,500 times E to the 0.072 times 15th power. Notice it's a little bit more than that 73.37. It's 73.61. $7,361.70 because I round that up to 0.70. Okay, so that's my future value there. Finally, we're looking at an exponential regression equation. Let's look at the cost of college. Cost of college tuition. You probably have not met me. Mr. Jensen, I graduated high school in 1984, and I went to college beginning in 1984 when college was a lot cheaper. Back then, for a public college, I did not myself go to a public college, but public college back then for a 4-year college, the cost of tuition, now this is tuition, it doesn't include room and board, was $1,228 a year. And you can see how the average cost of a 4-year public college has increased in tuition from 1984 every 5 years to 2019. I want to use the TI 84 to produce a scatter plot. Now what I'm not going to do is I'm not going to use the years 1984, 1989, 1994, and so on. I'm going to let 1984 be year 0. And then you'll notice that every year, 1989, 1984, I increased by 5 years. So I'm going to use 0, 5, 10, 15, 20 for my X values to represent the number of years since 1984. So just like we've done regressions before, stat edit, I'm going to put my X values in L1, 0, 5, 10, 15, 20, 25, 30, and 35. In my L list, I'm going to put the cost of tuition for each year, 1228, 1780, 2681, 3349. You can see the numbers there. I'm not going to read them all to you. Okay, so now I have all my values in there. Draw the scatter plot. Second stat plot. We're going to select number 1 and press enter to turn the plot on. we're going to ensure that that this is on scatter plot. X list is L1, Y list is L2. As I've mentioned in other videos, I prefer to use the plus. Then all I need to do is go to zoom, number 9, zoom stat. Whoops, let me get this out of here. I've got a couple of things in here. And you see the rising cost of college. Okay. Zoom 9, make sure that that's on zoom 9. And the cost of college has been increasing fairly significantly. That data looks more exponentially. Is a linear model good for this data? No, because the cost of college has not been increasing at a constant amount. It went up $500, then $900, $700, $1,700, $1,800, $800. That rate of it, that amount of increase has not been consistent. So let's look at part C here and find an exponential model for that data. Stat, calc. In my video on linear regression, we went to number 4 for linear regression. For quadratic regression, we would go to number 5. If I was doing a cubic or quartic regression, I would use 6 or 7. Number 8 is a linear regression, the form that we use for statistics. I'm going to go down to number 0, the exponential regression. I'm also going to store that alpha F4 in Y1. Calc, edit, and here's my regression equation. Notice it has y equals a times b to the x. A is 1362, which is not exactly the 1228 from my observed value, but it's what would be expected based on this regression equation, with a b of 1.062 to the x. Okay, so my regression equation is estimating an initial cost of 1362 with a b value of 1.062. That means that college has been increasing at an estimated annual rate of approximately 6.2% per year. Okay. Use the regression model to estimate the cost of college in 2024 and again in 2034. I would go back to our table, right? And I've shown you before to go to second table set the independent variable to ask. That way, when I go to my table, it's blank, and I could say, let's use 2024. Of course, 2024 is 40 years after 1984. So we're going to use 40. So I would estimate that the cost of college now is $15,034 at a 4-year public school, just for tuition and fees now. For 2034, that's another 10 years into the future. I would estimate the cost of college in 2034 to be $27,402. Okay? And so there's our look at exponential regression. We've looked at the exponential functions, just like in a previous video. We looked at quadratics, and before that, linear. Again, I hope that this has been helpful. If you do find these videos helpful, I would appreciate it if you would like or subscribe to these videos on the YouTube channel. And I look forward to seeing you next time.